today we're going to talk about graph theory for fun. And so a graph is, let's call a graph G, is a collection of points, V. So V is a set of points called vertices, and a collection of a set E of edges. Okay, of these lines that connect a pair of vertices. Okay, so if you have two vertices in V, you could either have one line, or I guess you could define it in such a way that there's more than one edge connecting two vertices. There's all different types of shapes and sizes of graphs. So we'll look at some examples. When I say the order of a graph, I'm talking about the number of vertices. When I talk about the size of a graph, that means the number of edges. Okay. If two vertices are connected with a line, we say that they're adjacent vertices. And then if you count the number of edges that are connected to any one vertex, that's called the degree of the vertex. Okay? All right. So here's some examples. Let's go here. All right. So let's look at an example. You can label graphs. You can label vertices with letters. Greek letters. You could have look at these three graphs. So when you say line, you often mean a straight line. But then I didn't say you had to be a straight line. Sometimes it's impossible to draw the graph with all straight lines, so you might have to go around. Sometimes. Some graphs you can use loops. You can have like a vertex connected to itself. But today I'm just going to focus on the most basic type of graphs, undirected, so that there's no arrows on any of these lines. And I'm not going to do anything where I have loops, like any vertex connected to itself. I'm not going to have more than one vertex from one point to another. So I'm not if like A and B are adjacent, I'm not going to have one edge from A to B. Okay, I'm not going to have 2 or 3, whatever. Okay, so these are examples of graphs. You got points and you got lines. So all three of these graphs are isomorphic. They're essentially the same. I just relabeled them and drew them differently. But you see how they're all the same. They're all equivalent in some way. Right, you got like one vertex that has 3 edges, and you have 3 vertices with only 1 edge. So if you look at these 3 graphs, they're all equivalent. Okay, so that's one thing when we talk about in topology or things being topologically equivalent, or in graph theory you can say they're isomorphic. It means that they're basically the same shape. Okay. All right, so I might use that word for these 3 graphs are isomorphic. They have the same structure, but they just look different the way I drew them. Okay? The edges you can rename the edges, and so you might say edge AB. So edge AB is just like edge alpha beta here. So I just relabeled it and repositioned and stuff, but they're essentially the same structure. Okay. How about another graph? So look at this graph right here. So what is the order of this graph right here? So I define the order as to be the number of vertices. So how many vertices are there? These dots are the vertices. 1, 2, 3, 4. Very good. What about the size? So you don't have to have a line connecting. And so this vertex here is like hanging out by itself. That's okay.
Vertices is the plural
So
vertex.
Vertices is the plural of vertex. One vertex, many vertices. So what is the size of this graph? There are 2 edges, so its size is 2. You could say that vertex A is adjacent to vertex B. Or things like C is not adjacent to D. There's no line. What is the degree of vertex A? The degree of vertex A is 1. There's 1 edge. What about the degree of B? The degree of B is 2. What's the degree of C? 1. What's the degree of D? 0. Right? So add up all these degrees. What do you get? 1 plus 2 plus 1 plus 0. You get 4. Well, it's actually a theorem. I guess one of the first theorems will prove that if you add up the degrees of all the vertices, it's always going to be even. Believe it or not. So that's called handshaking law.
So it is just a coincidence that adds up to the
That adds up to the order? Yeah. Yeah. Just coincidence. Okay. All right. Let's talk about some other work. There is no edge connecting vertex B. So we say vertex B is isolated. Can't get there from here. All right. Explicitly forbidden. All right.
I think that would be loss of generality.
All right. What's the size of this graph?
Size?
Size is 0. So there's no edges. We call that a null graph. Not particularly interesting. So remember, if we talk about like handshakes, like if you two dots represent people, and an edge represents handshakes. This is like math club party. I'm not gonna shake his hand. So now, and you go to fraternity parties, exact opposite. Everybody's shaking everybody's hand, or there's some other kind of physical contact going on. So what if we had a graph like this?
A little bit of sense to that.
Yeah. Except for trying, not sorority. So what if you had? So now every edge is connected to every other. Sorry, every vertex is connected to every other vertex. And remember, I'm not gonna put more than one line, connecting any two vertices. So this is actually called a complete graph. Complete graph. In some sense, it's complete because you can't add any more edges. Okay. So a complete graph has all, you know, you can do a complete, this is a complete graph with 3 vertices. A complete graph with 4 vertices would look like that. I can't, every vertex is connected to every other vertex by an edge. So this would be a complete graph with 3 vertices, a complete graph with 4 vertices, a complete graph with 5 vertices. Like that. So these are called complete graphs. So remember one of the kind of examples I mentioned, if there's imagine there's 5 people show up at a meeting, and you go to a business meeting. There's 5 people, and everybody shakes each other's hand. Okay, and how many handshakes are there? Well, equivalently, you could say how many edges are there in the complete graph with 5 vertices. So counting, a handshake you could represent by an edge. It's not two vertices. So if you can count the number of edges of the complete graph, you can answer questions like about handshakes. So these complete graphs are often denoted by this Kn, where n is the order of the graph, how many vertices. Okay, so the Kn would be the complete graph with n vertices. Okay, so this would be K3, this is K4, this is K5. Okay. Why do they use K instead of C? Maybe complete in German it starts with K. I don't know. Well, so K for complete. So how many edges does? So it's, I showed this example. So if there's five vertices, this graph, this edge, if I start here and go around and count the edges, there's 4 edges from this vertex. If I go to this one, I need to count 3 of these edges that I haven't counted already. From this edge, I'd count 2 more, and from this edge, I only count 1 more. So for K5, you could count the number of edges as 4 plus 3 plus 2 plus 1. So you see this nice little formula for the edges kind of merging. The number of edges of the complete graph with n vertices would be, so the number of edges of Kn would equal, well, you can do n minus 1 plus n minus 2 plus all the way down to plus 3 plus 2 plus 1. Okay, so there's a better formula for that. It's going to be n times n minus 1 over 2. Okay. So like the number of edges for K5, the formula says it's going to be 5 times 4 divided by 2. So 20 divided by 2 is 10. Is that right? 4 plus 3 is 7, plus 2 plus 1 is 10. So there's a nice little formula.
It's still 5 choose 2.
Mm-hmm. Yeah.
So we can say that I'm sure there's a proof that proves that equation is equal to n choose 2.
I mean, that's the definition of n choose 2. But I haven't defined binomial coefficients, so that's why I didn't say n choose 2. So yeah, it is. So I mean, if you have any experience with binomial coefficients, it's used for counting things all the time, and so it's not surprising probably at all that you're counting objects and it equals a binomial coefficient. Okay. All right. So that was in chapter 3. We didn't really talk about binomial coefficients in chapter 3. Think we can prove this?
No.
The number of edges of the complete graph with n vertices is n times n minus 1 over 2. I mean, I showed you it with one example, so that's obviously a proof, right? One example is good enough. Right? Hopefully, if you learn anything in this class, one example is not a proof. Okay? Now, an example, a counterexample can disprove a statement, but one example does not a proof made. Okay? So, the number of edges of Kn is n times n minus 1 or 2. This is for all natural numbers n. What kind of technique do we use to prove a statement was true for all natural numbers? Induction. Yeah, you can prove this by induction. Okay. Let's do it. So you see how this graph theory would fit into a class like discrete. You have some new definitions, you have some new little theorems, and you prove them using the techniques we learned in this class. Okay, so like proof by induction. Okay, so let's see. That would be good. All right. We're trying to prove that Kn has n times n minus 1 over 2 edges. By induction. All right. So how does the proof by induction start?
Simplest case.
The simplest case would be when n is 1. Okay? So, what does K1 look like? It's the complete graph with one vertex.
0.
There's the graph, K1. Just one vertex, no edges. Okay? You have to have at least two vertices to have an edge. Okay? So K1 looks like this, and has 0 edges. Okay, and so 1 times 1 minus 1 over 2 equals 1 times 0 over 2 equals 0. So statement is true. For n equals 1. Okay, so this only works for n equals 1. When n equals 1, this is 0. And K1 does have 0 edges. Okay? All right. So now, we're gonna the inductive step, that was like, we call that part 1. We number these 1 and 2, I can't remember. But, so now we need to assume, so suppose K, now it's kind of weird with a little K, I guess, but let's use X. So I'll use kind of cursive lowercase k. Case of K has K times K minus 1 over 2 edges for some natural number K. So what do I need to show? I need to show the statement is true that forces the statement to be true for K sub K plus 1. So think about it. I need to show that K sub K plus 1 has K plus 1 times K plus 1 minus 1 over 2 edges. That's what I need to show. Right. So if I replace n with K plus 1, it will look like that. So that's what we're going with. All right. All right. So if K sub little k has k vertices, So think about this. How can I change the graph of k sub k to the graph of k sub k plus 1? Well, I need to add one more vertex, and then I have to connect that vertex to every one of these k vertices. Make sense? Okay? So to get the graph of k sub k plus 1, add one more vertex, and then connect it to the other k vertices. How many more edges will I have to add to connect it to k vertices? K edges. If I have, if I have 10 vertices and I have to connect one dot to 10 vertices, that's going to take me 10 edges. So if I have k vertices and I need to connect one vertex to these k vertices, I'm going to have to use k more edges. Okay. So if I start with, I know how many vertices I know how many edges this graph has. This many. Okay. Then to get the graph of k sub k plus 1, I need to add one more vertex and connect it to the other k vertices with k more edges. Okay? You see where I'm going?
Exponential.
So k sub k plus 1 will have this many edges plus k more. So then k sub k plus 1 has k times k minus 1 over 2 plus k edges. And that should equal what we want. We just got to get it in the right form.
So we need like
Okay.
this.
So to get this graph, I take the edges of k sub k and add one more vertex, and that's going to force me to add k more edges. But k times k plus k minus 1 over 2 plus k, get a common denominator, this equals k times k minus 1 over 2 plus k over 2. I can add these now, and
Plus 2k.
sorry,
Yes.
thank you. So let's see here. So I add this. So I get k times k minus 1 plus 2k all over 2. So I multiply this all out and then factor, I guess, k squared. I get k squared. I have minus k plus 2k. That equals k squared plus k over 2. Does that equal what I need? So this is, k plus 1 times k over 2, but this is the same as, maybe one more. I'm kind of out of range. Oh, you can still see that on the phone. So technically, to look exactly like the formula, it would be k plus 1 times k plus 1 minus 1 all over 2. All right. So concluding, so by induction, the theorem is true. Okay. So the complete graph with n vertices has n times n minus 1 over 2 edges. Next theorem is called the handshaking lemma. Okay, it says, for each graph, the sum of the degrees of the vertices is even. So think about how graphs can represent handshakes. So you can represent a handshake between two people as each person is a vertex, and each handshake is represented by an edge. So if you look at any graph and you add the degrees of every vertex, you always have to have an even number. Basically, what that says is, if you think about a handshake, how many hands are needed to make one handshake? Two hands. And so if you count up the degrees, you're going to be counting each edge twice. It would count when you add the degrees of all the vertices. You count that same edge for each vertex that's connected to. So when you count, you're basically counting each handshake twice, and you're adding up all the degrees of the vertices. So that's why if you're counting something twice, and you're always going to get an even answer. So I'll show you an example of a graph where we added up all the degrees, and it just happened to be 4, but it always has to be an even number. That's what the handshake on it says. Okay, proof. So each edge is connected to exactly 2 edges. Okay, so when we add up the sum of the degrees, so when we add the degrees of all the vertices, we are counting all the edges of the graph twice. Make sense? Because if you remember, the degree of a vertex is how many edges are connected to it. Well, if I count up, in the degree of one vertex, each one of those edges is also connected to another vertex. And so when I count the degree of that vertex, I'm also going to count that edge again in its degree.
So yeah. It's connected to exactly 2 vertices?
Yeah, sorry. Is that what you're going to? Yeah, sorry. Thank you. So each edge is connected to exactly two vertices. So when we add up the degrees of all the vertices, we're going to be counting that edge twice. For each vertex, that edge is going to count into that. It's going to add a 1 into that degree. Okay. So when I add up all the degrees, you're counting each edge twice. Okay. So we see that the sum must be even, and further, it's equal to twice the number of edges. So not only is the sum of the degrees always even, it actually always equals twice the number of edges. So maybe a quicker way to add up the degrees of all the vertices, you just find the number of edges and multiply by 2. Corollary. You don't remember what the word corollary is used for? It's a result or a theorem that follows directly as the consequence of a previous theorem. So corollary, Kn has n times n minus 1 over 2 edges. So instead of proving this by induction, I could have just waited and proved it using the handshake lemma. So think about this. Here's the proof. Kn has n edges, sorry, n vertices, each with degree. What's the degree of each vertex?
2n.
That's
Wow.
2n.
1/2.
So if you have n vertices, how many edges would be connecting that each vertex? Not n over 2. N minus 1. So if each vertex is connected to every other vertex, then each vertex is connected to n minus 1 other vertices. Okay? So Kn has n vertices, each with degree n minus 1. Right? Say if there's 10 edges, 10 vertices, then each one has 9 edges connected to it. If there was 100 vertices, each one would have 99 edges connected to it.
They don't count themselves.
You can't, yeah. So we're not going to have any loops where any vertex is connected to itself. So Kn has n vertices, and each one has degree n minus 1. That just means it has n minus 1 edges connected to it. Okay? Well, let's add up. Find the sum, right? The sum of all degrees equals, well, I mean, it's n minus 1 times n. So basically I'm done because what we just proved by the handshake lemma is that this has to equal twice the number of edges. So therefore, what does it say? This equals twice the number of edges. So how many edges does it have? N times n minus 1 divided by 2. Therefore, Kn has n times n minus 1 over 2 edges. Which proof do you like better? Induction or using the
Lemma.
handshake?
Lemma's more writing than.
Well, yeah, but now you have two theorems for the price of one, right? I have one other proof I wanted to show you by contradiction. So yeah, got enough time, I think. Yeah. What do we use? We use induction, we use direct proof. Now, how about proof by contradiction? It's good, maybe good practice for the final exam when you might have to do such proof techniques. All right. So I didn't define a simple graph, but I kind of, that's what I've been using. Simple graphs have no loops, no vertex is connected to itself, and you're not going to have multiple edges connecting the same. There's not more than one edge between any two vertices. Okay, so I've kind of, those are the only graphs I've considered today. But but you can have, so some people call them simple graphs. Okay, so theorem: every simple graph, so no loops and no multiple edges between two vertices. Every simple graph of order n, which is greater than or equal to 2, has two vertices with the same degree. So think about this again. If we would reinterpret this using handshakes, think about that. At a party, if you had, say, you had 100 people, and some people shook some other people's hands, and some people didn't shake other people's hands. Well, by this theorem, we can prove that there has to be two people at the party that have shaken the same exact amount of hands. So, is that obvious? I mean, suppose you go to a party and there's 100 people there, and after the party, you could guarantee that there were two people that if you ask everybody to write down how many hands did you shake at the party, two people would have exactly the same amount of handshakes. That's what it says. Right? If they have the same degree, then they have the same amount of handshakes. All right. Proof by contradiction. So, for the sake of contradiction, suppose G is a graph with order n greater than or equal to 2 with no two vertices with the same degree. Okay. Well, each vertex can have, at most, n minus 1 edges connected to it. Okay, so that's, I'm assuming that's, again, it's a simple graph. You're not going to have, you can't have loops connecting them to themselves, and you're not going to have more than one, you can't have more than one edge connecting two vertices. So at most, a vertex can have n minus 1 edges. Right? If there's n vertices, any one vertex can have at most n minus 1 edges. Is that clear? Okay. So the degree of any vertex has to be in the set. Well, what's the smallest the degree can be for a vertex? 0. You have no edges, right? So it has to be in the set 0, 1, 2, up to n minus 1. Okay, those are the only possible values for the degree of any one vertex. Okay, believe that? All right, I mean, we're saying the degree could be as small as 0, but no bigger than n minus 1. Okay. All right. Here's the idea. How many numbers are in this set? There's n numbers in this set. 0, 1, 2, 3, 4, all the way up to n minus 1. That's n numbers. There's n vertices. And I'm assuming they all have different degrees, right? That means that every one of these orders, every one of these numbers has to be a degree of a vertex, right? If I have n possible values and each vertex has a different one of these different value, then I've got to use all of them. Okay, that's not reasonable. But here's the contradiction: you can't have a point with order n minus 1 and a point with order 0 or degree 0. Because if the degree is n minus 1, it's connected to all the other points. But if the degree is 0, it's connected to no other points. You can't have both things going on. Okay, so that's the proof here. Okay, since there are n vertices, all with different order. That was our assumption. To get our contradiction, we assumed they all had different degrees. So all with different degrees. And so there's n vertices, all with different degrees, and only n possible degrees. Okay, makes sense? There's n vertices, they all have different degrees, but there's only n possible degrees. Then there has to be one vertex with degree 0 and one vertex with degree n minus 1. Right? So there's n vertices, there's n possible values for the degrees, and each one has a different degree. Then one has to have degree 0, and one has to have degree n minus 1. This is a contradiction. Okay, do you see why it's a contradiction? Because degree 0 means it has no edges connected to it. Degree n minus 1 means that vertex is connected to every other vertex. You can't have both. Okay. So this is a contradiction. I have to go further and explain why it's a contradiction. This degree 0 means it's not connected to any vertex, but degree n minus 1 means it's connected to every other vertex. You can't have that happen. Both those things can't happen in the same graph. So, I'm interested in just kind of stopping here. I think we're close to 240. We'll stop there. So this is, I hope you get the flavor of graph theory. And also, you can see how the proof techniques, there's no proof techniques that I did today that you haven't seen before. There's contradiction, induction, some direct proofs. And so that's kind of the reason why graph theory would be included in this course. Okay? But, I think we're enough with what we have so far.